So in the last video, we were introduced to this idea of modeling periodic motion or oscillatory motion, basically motion that can be described by sort of a repeating pattern of waves. And we were introduced to using sine and cosine and talked about frequency, which is, the amount of cycles we can squeeze into 1 second. We refreshed our brains on what period is, which is the amount of time it takes to complete one cycle, which is the reciprocal of frequency. And all of the examples that we dealt with, whether we were talking about, the weather going from high to low and low to high, or a box attached to a spring kind of going back and forth, no matter what example we did, we never had to worry about the motion dying out. We just said, oh yeah, the spring will oscillate back and forth. Oh yeah, the weather, the temperature will just go back and forth, just like so. But in the real world, if you heat up a coffee mug or something, it'll get hot and then it will kind of slowly dissipate down over time. Or if you have a spring attached to a box, it would go like this and it would go boing, 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 and then it would come to rest at equilibrium. And so we're going to talk about what this thing is called damped harmonic motion and kind of how we go about modeling it using trig functions. And it's actually very simple. It's not too bad. But first, let me provide two definitions. So a definition, first we need to define harmonic motion. So harmonic motion. Harmonic motion is a type of periodic or oscillatory motion. And harmonic motion just means, is a periodic motion. Okay, harmonic motion, it's a periodic motion, and the idea is that, maybe the best way to describe this is to think like a spring, where if I have a spring attached to a box, okay, and I pull the spring all the way out, this is harmonic motion because the amount of force being exerted on the box by the spring, the amount of force that's, pulling against you as you stretch this spring out, increases. It increases in some fashion due to how far you've pulled it out, right? So for instance, if the box is at equilibrium, there's no force being exerted, but the further that I stretch this box out, the more force that this spring exerts. And then, of course, as you compress the spring and the box ends up here, again, there's some distance that we have traveled from equilibrium, and the more force that the spring is going to exert out that way. So harmonic motion is the idea, it's a periodic motion where the force exerted on an object, exerted on an object increases based on the object's distance, or displacement, we'll say, displacement from equilibrium. Okay, so this type of motion it is just a type of periodic motion. Okay, so all it means is that if the box is at rest right here in the middle, and you pull it, right? You pull it all the way out here and you let go, the box is just going to go wee, right? It's going to keep going on forever and ever and ever. Nothing is slowing it down. We're assuming nothing is what's called dampening the motion, okay? It's just, it is its own self-sustaining system, and the spring never dies, right? We never lose any energy. But we know that that's not entirely true. We saw, like, sure, yeah, you could model this, okay? You could model this using something like a sine of, b t plus c plus d, right? We can model it using this, or we could use cosine, right? We could use a cosine of b t plus c plus d, right? We can use either one of these. But in reality, we know that, over time, if we let go of that box, eventually it's going to, it'll oscillate back and forth and back and forth and back and forth and back and forth and back and forth. And then it should come to rest right at the equilibrium. That's what should happen. And so the question is, how do we take into account damped harmonic motion? So definition, damped harmonic motion. Damped harmonic motion simply indicates that our system, we call, like the box being attached to a spring, a system, that our system loses energy in some way. Loses energy in some way. And will eventually come to rest. Okay, so this kind of seems to make a little bit more sense. More interesting question is, well, how do I take into account the fact that if we talk about, non-damped harmonic motion, non-damped harmonic motion on a graph might look something like this, where maybe we stretch out the spring a certain way, we let go, and it just keeps going forever and ever and ever, okay? Versus damped harmonic motion, which is going to look, as we've said, I don't know, something very roughly like we pull it, we release, and it goes like this, and then it just kind of peters out, okay? How do we talk about one versus the other? Well, in the one on the left, they both have the same period, okay, because the box still goes back and forth, right? Okay, they still have the same period. They were going to, they both start at the same place, so they both have the same horizontal shift. They're both going to have the same vertical shift. What is the only thing that's changing in both of these graphs? Well, the only thing that's changing in both of these graphs is the fact that the first one maintains an amplitude, and the second one experiences a kind of a decline of amplitude, right? The amplitude starts to decline, okay? And so the idea is, to model damped harmonic motion. Damped harmonic motion. Okay. We, consider, let's start with cosine. Cosine's a good one. So let's just consider that our function that represents the height of our box or whatever it is it's our A cosine of, B times T plus C plus D. But let's say that there's something else here that's being multiplied. Okay, there's something else here that is causing our amplitude to shrink over time. Okay, amplitude to shrink over time. Okay. And what could this be, right? Well, it kind of depends. So let's give an example. I think examples are the best way to learn about anything. So for example, let's pretend that let's see, what can we do? I think I have a pre-made example already. Okay, so let's see. You pull a spring. Let's see. You pull a 10 centimeter spring. Let's see, 4 centimeters past equilibrium. And release. Okay. Let's see. After 1 second. After 1 second. Okay. The spring is only stretching out 3 centimeters past equilibrium. Okay. So if the spring is oscillating up and down, the spring is moving up and down. How many times do I want? We could just say like 5 times per second. You know, model the motion of the spring or the position of the box. Okay, so let's try and wrap our heads around what's going on over here. Okay, so we have a spring that naturally kind of rests, we'll say, at 10 centimeters. Okay, this is 10 centimeters. We, of course, pull it down a little bit further, stretch it out. Okay, so it goes down to 14 centimeters. It oscillates up, down, up, down, up, down, up, down, up, down, right? 5 times, okay? When we measure it again, right, when we take a look at it, now the box is only at 13 centimeters. Okay, it's only going 3 centimeters past. The question is, how do we model this? Well, let's see. If there wasn't anything dampening our motion, right? If there wasn't anything slowing down, based on everything we learned in our last video, we might say that, you know, that if I were to just create a very rough sketch, okay, I might say, okay, well, we pull it down to minus 14. It has equilibrium down here at like minus 10. That means it's going to bounce up to minus 6. And then, you know, it starts down at 14, and then it's going to go up, and then it kind of goes down, and it's going to go up, right? And so this, if we weren't taking into account the fact that the motion is going to die off, it would just look like this. Okay, and that graph right there is simply minus 4 cosine of something with a t, right, of bt, because there's no horizontal shift, and then it has a vertical shift of minus 10, because that's where equilibrium is, right? Our midline kind of goes right through the middle here. We have dropped down 10 units. So how are we going to figure out that b term? Well, in order to figure out that b term, we know that the frequency, right, the number of cycles that we fit into a second is 5 cycles per second. And we know then that the period is the reciprocal of that. It's going to be 1/5 seconds per cycle. Right, that's period. And we can use that because with a cosine graph, we know that 2 pi over b should equal 1/5. So again, multiplying both sides by b and 5, we immediately get that b is equal to 10 pi. So I'm going to go ahead and erase this little bt term, and I'm going to put in 10 pi times t. Boom. This is what our equation would look like if we weren't slowing anything down, right? If we weren't dampening it. Now, the question is, you know, we are dampening it. We saw that it kind of died out. It says that it's only stretching 3 centimeters past the equilibrium after 1 second, right? So it happens pretty quickly here. So how do we do that? Okay, so what I'm going to do is I'm going to interject something here. I'm going to erase that minus 4. I'm going to put it way out in the front right here, minus 4. And I'm going to put something in the middle here that is going to, you know, cause our amplitude to decline. Now the question is, you know, the really important question that we need to answer is, you know, after 1 second, you know, how much of our amplitude do we have left? And this is kind of a weird question, but I'll say it anyways. How much of our amplitude do we have left? Okay, because if you remember, so maybe I'll do an aside over here. This will be a nice little recap. Where should I do this? Over here. I'll So back in pre-calculus 1, we used to do examples with bacteria, and we used to say, you know, if you have one bacteria, and then you have two bacteria, and then you have, I guess not multiplying, maybe just an arrow, and then you have 4 bacteria, and then you have 8 bacteria, and then you have 16 bacteria, and you're like, if every time you're doubling it, right, you have twice as much as what you started with, you could indicate this by saying, you know, that every second you'll have 2 to the t bacteria. This was like exponential growth, if you remember, okay? And then likewise, let's say you had 16 bacteria, and then eventually you had 8, right? You had half of that. And then you had half of that, and then you had half of that after some time, and half of that after some time, and so on and so forth. You could represent this by saying, well, I'm going to have half the bacteria, and, you know, like how long is it going to take? Well, half the bacteria every second, right? So just like so. And notice this doesn't equal 16. What we need to do is put like a 16 in front of this. So when t is equal to 0, we're going to have 16 bacteria. But when t is equal to 1, we're going to have half the bacteria. And when t is equal to 2, right, then we're going to get 1/2 squared, which is a fourth, and a fourth of 16 is 4. Right, so t equals 2, t equals 1, and so on and so forth. So this is how we would represent something like that. So in our example, right, going back to our example, we know that we start with 4 centimeters. And after 1 second, we have 3 centimeters left. So in other words, after 1 second, we have, you know, 3/4 of our original amplitude. And we assume that this trend is going to continue. Why do we make this assumption? Well, because if the spring is slowly dying out over time, we're going to assume that this trend is going to continue because we're not modifying the system, right? We're not injecting it with energy. We're not touching it again. It's just doing its thing. And so how do we indicate that? Well, just like with the bacteria up here, we're just going to put a 3/4 to the t right there. And that basically says, you know, that when t is equal to 1, what is our amplitude going to be? Well, it's going to be 3/4 of whatever this amplitude originally was. And so 3/4 of 4 is just 3, which should make sense. And as we increase t, right, t is 2, t is 3, etc., that is going to cause our graph to decline. Okay, it's going to cause our amplitude to decline. Okay, and let's think big picture. Okay, so let's talk about this model that we have. -4 times 3/4 to the t times cosine of 10 pi t minus 10. All right, let's talk big picture for a second. Okay. Remember how I said that this models our movement of our box. So it starts low, goes like this, and I claim that, you know, we just keep killing it, and eventually it comes to rest. Now, where should the box come to rest at? Well, it should come to rest at our midline, right? It should come to rest at 10 centimeters down because that's the box is hanging down. Cool, great, okay. Let's see if that makes sense. If I let t right here, if I let t get bigger and bigger and bigger, so equals 10, and then 100, and then 1,000, and so on and so forth, as it gets bigger and bigger and bigger and approaches this number, which you may or may not have heard of before, but as it approaches infinity, what is happening to the value of 3/4? Okay, what is happening? What happens if you take 3/4 and you multiply it by 3/4, and you multiply it by 3/4, and you multiply it by 3/4, what's happening? And you do this again and again and again. Break out your calculator, try it out. You'll notice that it is getting smaller. Okay, it is getting smaller. And actually, eventually, if you do it enough, the idea is that this thing is going to go to 0. And if you believe that, right, if you keep multiplying 0.75 times itself a bazillion times, or 3/4 by itself a bazillion times, if this thing goes to 0, and it goes to 0, what happens to this entire quantity right here? Well, this entire quantity should go to 0, right? And what's that going to leave us with? It's just going to leave us with minus 10, which is where we said we should end up as time goes on forever and ever and ever. Okay, so hopefully this makes a little bit of sense. And so that is pretty much the idea behind damped harmonic motion. You basically just figure out how much you have left after a little bit of time, and so on and so forth. Now, let me point out some things. So one thing worth noticing is that, let's say, pretend we had 3 centimeters after 2 seconds. Okay, after 2 seconds. What would we have used to kill our amplitude, right? Because we had -4 cosine of 10 pi t minus 10. What are we going to put here? Well, we still have 3/4 of what we started with, but the question is, do I just put t? Because it doesn't, this right here indicates that every single second, when t is 1, t is 2, t is 3, we're losing a little bit, right? We're losing 25% of our amplitude, or that another way of saying that is we only have 75% of it left, right? We have 3 centimeters left. But that's not what this question says anymore. It says that we are losing it every 2 seconds. So what do? Do I put a 2t here? Well, what does this say, right? If I let t equal 1, how many times have we lost some of our amplitude, right? How many times do we only have 3/4 of it left? Well, if I do that, it's 3/4 squared, right? That's saying we lost 25% of it, and then we lost 25% of it again. So clearly that's not it. And so it actually turns out to just simply be t divided by 2. T divided by 2, like so. And so t divided by 2 works because you'll notice that, the only time that we actually get 3/4 here is when t is equal to 2. That gives us 3/4 raised to the first power. And so check mark, we are decaying at a really nice rate. We're decaying at the appropriate rate. Okay, so that's one thing. Another thing that you will see, and this is kind of important, is that in the textbook, instead of having something simple like this, instead of having it just being fraction raised to some power, okay, what they do here is they have a -4, they have a sine or a cosine function, 10 pi t, great, minus 10, but they have an e to the -rt here, okay? Now, there actually is a reason for this, okay? It's called damped harmonic motion because it actually experiences exponential decay, which, does look like this thing. But e to the -rt shows up because when you take a course called differential equations, the short answer is that this is extremely common and extremely used, and this notation here is much more common to see than seeing 3/4 raised to the t power. And so typically, what you'll have to do in your work is basically determine, how do you write 3/4 to the t? How do you write this like e raised to the -rt, right? How do we do this? And it actually turns out that it's not very hard. So, I'll do one example, just using the example we did, right? So to write, let's say we do all of our work and we figured out that our dampening constant here, our dampening coefficient, was 3/4 raised to the t power. But the textbook wants us to write it as e raised to the -rt, right? How much work do we need to do here? Well, let's see here. First and foremost, they are both being raised to the t power. So if you think about it, you could take the square root with the tth root of both sides, and what we would get is that we get 3/4 is equal to e to the -r. And now the question is, well, okay, so all I need to do is figure out what my r is, and I'm done, right? E is a number. We learned this in Precalculus 1. It's like pi. It's like 2.7 something. So how do I figure out what r is? Well, this is where reviewing your logarithms is very important. We take the natural log of both sides, right, equals the natural log of e raised to the negative r. And we start using some of our log laws, one of which is that here this is equal to negative r multiplied by the natural log of e. And then the natural log of e is just 1. So this is negative r is equal to the natural log of 3/4. And so we get r is equal to the negative natural log of 3/4. And usually in the textbook, they have you take this number, whatever this is, and they usually have you round it to a decimal. Now, if you've noticed my grading, I am not a fan of decimals, okay? I don't personally like decimals very much because they're estimates, right? As soon as you plug that into a calculator, it gives you an estimate of what the answer is. Me personally, I prefer, and will take on any quiz or exam something like 3/4 to the t, because as soon as you put in natural log of 3/4, actually, let me calculate it. Natural log of 3/4, okay, is roughly equal to negative 0.28768. Okay, so with a negative in front of it, this is going to be 0.28768. Now it keeps going, but if I were, trying to come up with this equation, option one is that our equation looks like negative 4 times 3/4 to the t cosine of 10 pi t minus 10. That's option 1. Nice, neat, easy. Option 2 is we put it in the other form, which, yes, it will show up again in the future, but for now, right, and this is what's going to look like, negative 0.28768 t times cosine of 10 pi t minus 10, okay? Where this number here, right, this quantity with this variable up at the top, and this quantity right here with the variable at the top are the exact same. More specifically, if you're like, what? Just imagine they both don't have a t, right? What we just did is we said that 3/4 is the same thing as the number e raised to the negative 0.28768. That this is essentially what we have said. We have basically, for some unknown reason, decided to write 3/4 as this decimal approximation with base e. Now, again, there is reasons for this. I don't think they're really pertinent to our class, but I just wanted to show you because they do show up in the textbook, and some of the homework problems will ask you to write it in this form. But I will happily take you writing it in the form 3/4 to the t or something of that nature. So that's damped harmonic motion. That's pretty much everything for this week. It's not too bad. Yeah, so if you have any questions, let me know. As always, use the discussion board. I think I'm going to put out, actually, I don't need to put out any more videos. There's just 2 videos this week. It should cover everything. So if you have any questions or you want to see extra videos, let me know. Thank you all for checking this out, and I'll catch you all in the next one.